Okay, welcome everybody. Thank you for being here. I'm just going to say a few words to start off the talk, our final talk. My name's Stephen Hegedus. I'm the director of the Kaput Centre, for those of you who don't know me, and welcome to the centre. This is the last talk of the first year of the centre's interdisciplinary colloquium series. And so this first year we have seen some varied and interesting talks which are all online on our website, starting back last year in October with Dr. Luis Moreno. Where is Luis? He's there. One of our own. Luis is a professor in the mathematics department here at UMass and a senior research associate at the centre. And we had Nick Jakeep come in to talk about dynamic geometry, specifically with Sketchpad, Barbara Doherty, Susan Jo Russell on early algebra. Barav Zimmerman came in last month from the University of Montana to talk about issues of social justice. And we conclude with Dr. Judah Schwartz on models for K-12 curriculum. I have some insight into what Judah has been thinking about recently, and I think it's going to be a really interesting talk. And he informs me he's looking for feedback or cricket bats.
Brickbats.
Brickbats. So, Professor Schwartz is currently a senior lecturer in education and research professor of physics and astronomy at Tufts University, where he directs a large NSF-supported project on science education for middle school and elementary school teachers. He is also an emeritus professor of engineering, science and education at MIT and an emeritus professor of education at Harvard Graduate School. Judah was trained in theoretical physics and mathematics and did research for some years in the area of atomic physics. Of course, that research, he and his colleagues developed a variety of computer graphics techniques that proved to be useful in the teaching of math and science. His current research interests include the design of software environments to improve the teaching and learning of science and mathematics, and the application of cognitive science techniques to the study of mathematics and science education. I was recently talking with Judah about his amazing background and his retirement, and I quote you, Judah, several times by saying retirement, that's something I didn't quite get right, as he continues to lead projects at Tufts, where he is at the moment. Judah has been an incredible influence to many people in the field of math and science education, and it is wonderful to have him here today in our centre to conclude the first year of our series. And I now pass it over to Judah to talk on formulating measures, a step toward understanding modelling in the K-12 curriculum. Thank you, Judah, for being here.
Thank you, Stephen. If you could make that talk to this instead of that.
Sure, that I can handle.
Let's see whether we can make this do talking to that. Not yet, but
Two-way communication. There you go.
there we go. And I suppose it might be helpful to shut the light, but I'm not certain that it will solve
Maybe.
the reflection problem.
No, that's not.
Okay, then leave it on. Fine.
It's a laser
A
projector.
couple of prefatory comments. One is that I feel particularly moved to be here because of the many years that Jim and I worked together, and jarring to know that he's gone, and and wonderful to celebrate the fact that his spirit lives on, and I thank you for being an institution devoted to preserving his spirit. So that's first observation. Second observation is that this work grows out of trying to understand. I have a nasty habit of trying to understand things that comes trippingly off the tongue of people, because it sometimes doesn't make as much sense as it should. Problem solving is one such word. It's used that way. In fact, it's even been turned into a verb, to problem solve, which I think is not only meaningless but a barbarism linguistically. And so in the course of running this project called the Fulcrum Institute, we devoted a lot of thought to the problem of modeling. And what does modeling mean? Certainly is very prominent in the rhetoric of mathematics and science education at all levels. And I thought it would be worth a think or two to understand what's involved, and possibly even to try and parse the act of modeling into what might reasonably be thought of as its component cognitive elements. So what I'm about to harangue you with is a sort of first go at what might be involved in formulating models, both in mathematics and in science, and I'll try and distinguish between them because they're not the same. So, that having been said, some vocabulary. Let me see if I can get this to talk to my machine as well. And that talks only to my machine, and that talks. Well, I guess we're going to do it that way. All right. So, what do I mean by a model? And I say that I'm asserting a definition of model for this purpose. Models are ways of relating the behavior of different measures to one another. And what do I mean by measures? And then what do I mean by this statement? For example, the force needed to stretch a spring is directly proportional to the amount the spring is stretched. That's a model. It's clearly not true, except over limited ranges, because it would imply that the more you stretch, the more it pulls back, and if you stretch infinitely, it pulls back with infinite force, and that means that no spring has an elastic limit. So clearly this model is wrong. On the other hand, it's immensely useful. But it's a model. Here's another model. The density of a block of matter is inversely proportional to its temperature. That's a statement about how density varies with temperature.